Okay, so then from this dispersion relation I am now going to come back to the original PDE that we are solving. So to do that, let us define a transformed coordinate. So transformed coordinate as follows. So I described my coordinates zeta as beta x minus c naught t, where I assume my beta to be much small, very small, or this is nothing but the same as my long wavelength assumption. So it's a this particular assumption is arising due to our long wavelength assumption to begin with. Okay. So long wavelength, let me call this as a long wavelength parameter. Okay. So that zeta is corresponding to my space variable, and for the time tau I have the transformed variable tau as beta square t. Okay. So when I use these transformed variable and convert this dispersion relation back into my PDE in the physical plane, I get the following PDE. Okay. So I am not going into great depth here, but I am just highlighting the type of equations that I am getting, and of course, where is the use of Hilbert transform in this particular example. So I get the PDE in this long wavelength scenario as follows. So I get eta of t plus c naught eta of x plus alpha of the Hilbert transform of eta xx is equal to beta square eta of tau plus alpha of eta of this variable zeta. Okay. So well, after changing this expression using my transformed variable, I get to this particular expression, and this is set equal to 0. So if I were to look at this particular equation in the transformed plane, this is the celebrated linear Benjamin-Ono equation. So linear Benjamin-Ono equation. Okay, so this is particularly useful to study deep water waves, where again my h of the function eta is defined as, so the second variable is t, is defined as my Cauchy principal value integral as before. So this is integral from negative infinity to infinity eta of x prime comma t divided by x prime minus x dx prime. Okay. So this is my Benjamin-Ono equation for the deep water case, where my variable eta is the depth that we are studying. So depth as a function of x and t, the ocean depth. Okay. So then moving on, there is the nonlinear version of, let us say this is my expression 5. So there is a nonlinear version of this equation 5. The nonlinear Benjamin-Ono. So the nonlinear Benjamin-Ono equation is described by this following equation. So eta of t plus c naught eta of x plus c1 eta times eta x plus alpha times h of eta xx, this is equal to 0. Notice that this is the introduction of this new term or the new nonlinear term, that is an extra term which is present in this example, and the corresponding solution to this equation was studied analytically and found that the corresponding wave solution is as follows. So this is given by a times lambda square divided by x minus c t square plus lambda square, where my c is, so where my variable c is given by these sum of two variables c naught plus half a c 1 and a lambda is equal to negative 4 alpha by C1. Okay. So, then so if I were to come back to my original model, my C naught in terms of my original model is given by this expression. C naught is the difference between the two densities as follows. So, this is the square root of this expression times G h, and alpha is rho 2 by rho 1 times h 1 C naught by 2. Okay. Okay. So, as I have discussed that these type of equations, this, let us say this is my expression 6, the equation given by 5 and 6 is studied in a large variety of physical problems. So, starting the applications include lot of areas, especially in quantum mechanics. So, in quantum mechanics, in optics, and people have been using these Benjamin-Ono, the linear and the nonlinear version regularly, in especially in these two areas that I have highlighted, and also other allied areas. Now, I am going to talk about another specific case of these deep and shallow water models. So, that is, well, the deep water model. So far I have introduced the deep water model. The second case I wanted to say a little bit about was the shallow water model. So, shallow water theory, again introduced by Benjamin, that was in 66. Okay. So, this theory was evolved slightly earlier. So, in this shallow water theory, again the assumptions are as follows. So, we assume that we have a long wavelength k going to 0, again the long wavelength assumption, and the disturbance scales, well, the long wavelength disturbance scales with the length. Okay. So, what it means is that I fix, so this particular assumption means that I fix my height given by h 1 plus h 2 and take this limit k going to 0. So, further, that is my first assumption. Further, I assume that my wave propagates to the right. Okay. My wave propagates to the right, which means that my dispersion relation is as follows. So, instead of an absolute value that was described in expression 3, I have this following expression, it is gamma times k cube. Okay. So, I have got rid of the absolute value and taken the cube. So, the absolute value is gone here. Okay. So, then what we have is that the corresponding, so if I were to transform, take an inverse transform of this expression. So, let me call this as expression number 7. So, if I were to take the inverse transform of equation 7, so the corresponding PDE is given by the famous linear PDE as follows. So, this becomes eta t C naught eta x plus gamma eta x third derivative. So, this k cube brings in a third derivative, and presence of 1 k brings in a first derivative, and of course, the omega means when we are transforming, that corresponds to the time derivative. Okay. So, we have the following PDE. This is again a linear PDE, and it is the linear Korteweg-de Vries equation, also called as the linear KdV equation. Okay. So, I am going to just give you the solution to this equation. Again, with appropriate boundary conditions and initial condition, the solution to this equation can be analytically found. So, I can provide you with the Solution, well again eta is the depth of the water wave. The solution is given in terms of a wave like solution as follows. So, this is eta of x minus C t is secant hyperbolic square of x minus C t by lambda, okay, where my C is given by this expression C naught plus A alpha by 3 and my A lambda square is 12 gamma by alpha. Okay. So that completes more or less completes my discussion on water waves. However, I am also going to talk about again another application of Hilbert transform in relation to these wave equations and other areas of where we apply these PDEs, especially aerodynamics and elasticity. So, then following in the same way, it was shown that there are some applications of finite Hilbert transforms as well. So, finite Hilbert transform. Okay. So, what I mean by that? Well, of course, the finite Hilbert transform. So, let us denote it by h of f. So, h of f of the function f of t, and now I have to give a finite limit of the integral a comma b. So, this is f hat h x a b and this is also equal to 1 by pi the Cauchy principal value integral, this time from a to b f of t divided by t minus x dt. Okay. So, instead of an infinite values of the integral, an infinite integral, I have a finite integral. Okay. So, then well, I am just going to highlight some of the applications. The students are encouraged to see the applications in these areas. It was first introduced by a scientist known as Tricomi in this year, where he utilized these finite Hilbert transforms in his problems related to aerodynamics. Okay. And then it was also shown in elasticity, applications in elasticity of membranes, elasticity of rods, and also in airfoil theory, airfoils by these people, Gekhoff. There was a paper published in 66 and by Peters published in 71. Okay. So, we see that without specifically solving some problems in Hilbert involving Hilbert transform, I have just highlighted some of the examples where Hilbert transforms are widely applicable. So, then I am going to talk about asymptotic expansions, and most important, I am also going to talk about one-sided Hilbert transforms, one-sided Hilbert transforms. Okay. So, what I mean by that is consider the Hilbert transform again. Consider the Hilbert transform of f, which is given by integral negative infinity to infinity f of t divided by t minus x dt. So, what I see that is this integral is, well, so I call this as the standard Hilbert transform or the two-sided Hilbert transform, two-sided Hilbert transform. Okay. So, then I am going to break this integral at point x equal to 0, and of course, we have to take care of any arising singularities in the appropriate integrals that arise. So, breaking down into two integrals from 0 to infinity f of t divided by t minus x, and then of course, from negative infinity to 0 f of t divided by t minus x dt. Okay, we see that this second integral if I change my variable t by minus t, I get that my new integral is integral from 0 to infinity f of t divided by t minus x dt minus integral. So, I am going to assume that my new set of two integrals are also principal value Cauchy principal value integrals, because we are not aware where is this x, is x positive or is x negative. So, then my second integral is integral from 0 to infinity f of negative t times 1 by t plus x dt. Okay. So, let me just absorb this minus sign inside the integral, and notice that this, to begin with, my two sided Hilbert transform is the sum of two one sided Hilbert transform. Later on I am going to show that this is another special integral transform known as the Stieltjes transform. The Stieltjes transform, okay, or this is denoted by this curly s of the function negative f of negative t. This particular Stieltjes transform is a one sided Hilbert transform. Okay. So, then let me just say that, conclude this part of the discussion by saying that my one sided Hilbert transform is defined as h plus of f of t equals this transform f hat of h. So, the plus denotes I am taking the positive integral in the positive domain. So, f hat of h, f hat h of x, this is also equal to integral 0 to infinity f of t by t minus x dt. Okay. So, then let us see some of the properties of this one sided Hilbert transform. So, in particular I have some result related to the asymptotic expansion of this Hilbert transform. So, the problem says prove the following expression. So, prove the following asymptotic expansion of one sided Hilbert transform. Okay. So, the expansion result is as follows. So, I have to show there are two results, that the Cauchy principal value integral of this one sided Hilbert integral of cos omega t by t minus x dt is given by asymptotically given by negative pi sin omega x minus summation n factorial by omega x to the power n plus 1 n from 0 to infinity cos n plus 1 times pi by 2, okay, and the asymptotics is in the limit x going to infinity. So, this is the asymptotic expansion in the limit x going to infinity. Now, the second result says that the similar integral sin omega t minus x dt is pi cos omega x minus summation again from 0 to infinity of n factorial by omega x to the power n plus 1 sin n plus 1 pi by 2. Okay. So, then the idea is to prove this result using my Cauchy's principal value theorem. Okay. So, sorry, the Cauchy's residue theorem, right. So, what I mean to say was that I am going to use my Cauchy's residue theorem to give you the answer to this proof. Notice that these two integrals are complementary in the sense that one is a one-sided Hilbert transform of cosine and the other side is the one-sided Hilbert transform of sine. So, if I were to look at the one-sided Hilbert transform of this particular integral from 0 to infinity e to the power I omega t divided by t minus x dt. If I were to evaluate this integral and separately look at the real and the imaginary part of this integral, that will correspond to the left hand side of the two expressions that I am trying to evaluate. So, all I have to do is to find the Hilbert transform, the one-sided transform of this particular integral of this particular expression and see the real and the imaginary part. So, moving on to find, so if to find or to evaluate this integral using the Cauchy's principal value. So, Cauchy's principal value. So, this is my Cauchy's principal value integral and using my residue theorem, I get that the answer to this integral will be 2 pi I times the residue. So, the idea is I am going to first change this one-sided Hilbert transform into two-sided Hilbert transform. Okay. So, we are going to take a limit. So, sorry, we are going to take the lower limit, extend the lower limit of the integral from negative infinity to 0 and 0 to infinity, and then the second step will be of course to use my Cauchy's residue theorem jointly with Jordan's lemma. Okay. So, as I have shown you in some previous examples, this particular integral on the real axis is going to change into a contour integral, which will be evaluated using residue theorem, and the contour integral has two parts. One is this real integral and the other integral is on the curved part, but on the curved part that integral will vanish using my Jordan's lemma argument. Okay. So, using all these steps I am going to come to the final form of the expression which gives me this result. So, I get the following: pi I e to the power I omega x plus the second integral is the real integral that I leave as it is. So, this is integral 0 to infinity e to the power I omega t divided by t minus x, okay, dt. So, this is the integral that we are trying to evaluate to begin with and taking the real and the imaginary part of this integral, and this first term is coming out due to the Cauchy's residue theorem. Okay. So, let me just rewrite this first term again. So, this first term is pi times e to the power I omega x plus pi by 2. So, I have absorbed this iota inside this exponential using my Euler's formula. Okay. So, then let us look at this particular integral. I call this as my integral I1. Okay. So, I1 is as follows. My I1 is integral 0 to infinity e to the power I omega t by t minus x dt. Okay. So, then this is also equal to, I am going to make a change of variable. So, I am going to change my variable t as follows. So, introduce IU instead of a t. So, I get that this new integral is integral from of e to the power negative u omega divided by, so instead of a t I have IU. So, x minus IU du, and I can pull out this negative I common, and taking the appropriate limits, this will also go from 0 to infinity. Okay. So, then what I have done is first made a change of variables, and also I have changed the integral from the negative to the positive. So, the earlier integral, this integral was on the real axis, right. So, I have further changed the integral on, so change I1 on the positive imaginary axis. Okay. So, imaginary axis. Okay. So, it was assumed that my original variable t was a real variable, and then I have changed it to another variable which is purely on the positive imaginary axis. Okay. So, I have done this transformation. So, then let us look at the expression. Well, let us look at this factor here. Okay. So, my I1 is negative I integral 0 to infinity e to the power minus u omega divided by x minus I u. So, I am going to take my x out of the expression. So, I get 1 by 1 minus I u by x, okay, du. So, I know that the binomial expression, the binomial expansion of this particular factor 1 minus I u by x is equal to the following series. So, I have summation n from 0 to infinity, I have I u by x to the power n. Okay. This is in the limit that mod I by u by x is much less than 1, or x goes to infinity. Okay. So, then only this binomial expansion is going to hold. Okay. So, then I am going to change this factor with this summation, and I am going to further. So, let me call this step as my step 1. So, in 1 my I1 now is seen as follows. I keep this negative outside. So, I have a negative. Now, I take the summation. So, I have already interchanged the sum and the integral. So, summation n from 0 to infinity, and then I have an I sitting here, and I to the power n will give me I to the power n plus 1, and then I have u n coming from here divided by x n times x. So, I n plus 1 by x to the power n plus 1 times integral 0 to infinity u to the power n e to the power negative u w or omega, and my integration variable was u. Okay. Here we have already interchanged my summation and integral. So, notice that this second integral, if I were to replace my variable, let us say y by u omega, then and use. So, after this substitution I can see that this particular integral is nothing but the gamma function. So, this is going to be the gamma function of n plus 1 divided by omega to the power n plus 1. Okay. So, then substituting that, I get that my I1 is negative n from 0 to infinity. I have, well, gamma of n plus 1, n is an integer, I get n factorial divided by x to the power n plus 1 omega to the power n plus 1. So, omega x to the power n plus 1 times I have I to the power n plus 1 here. So, I write it using my Euler's formula, this is e to the power I n plus 1 times pi by 2. Okay. So, then what I have is, so this is nothing but I to the power n plus 1. So, then I am already there in my result. I see that my, so my I1, I leave this expression as it is, and I come back to my original problem. My original problem was I am trying to evaluate this particular integral. So, my original problem, my integral to be evaluated is e to the power I omega t divided by t minus x dt, and this is equal to kept equal to pi I e to the power I omega x plus pi by 2 minus this infinite sum from 0 to infinity n factorial by omega x to the power n plus 1 e to the power I n plus 1 pi by 2. We see that this particular sum, we now take the real and the imaginary part of this sum and equate it to the corresponding real and the imaginary part of the left hand side, and we are going to arrive at our expressions, or both the expressions.